Here's a demo video of how we manufactured the power receiving coil with liquid metal. We used EcoFlex, which is an easily accessible silicon molding material. We chose silicon because it's non-toxic, flexible, and is widely used in medical applications. Within the substrate is silicon tube of 2 mm diameter in spiral shape. Here's a picture of the tube embedded in the cured silicon substrate. The mold was 3D printed. For the prototype, the power coil has 10 turns to achieve optimal power efficiency and a reasonable size. The tube and silicon substrate were cured for 5 hours. What goes in the tube is liquid metal, which is gallium indium alloy. We use a hot plate to melt and mix the metals, and the alloy stays as liquid at room temperature. Here's a picture of the liquid metal in the glass vial. It also forms an oxide layer, which helps to keep the form and prevent leakage. We use a syringe to inject the liquid metal and test it for resistance, and sealed the opening with silicone. This component is extremely flexible. You can bend it to any angle. It conforms with the skin and is lightweight and more comfortable than rigid wearables.
This is a demo of our testing circuit, which uses a LED as a load. The testing board is connected to the liquid metal coil. As the transmitter coil approaches, the LED lights up. On the real sensor node, the same circuit is used. You can almost see a tiny surface mount LED lights up as the transmitter approaches, which signals that the board is charging. Now I introduce the technical details of the circuit board of FlexiSense. Here you can see the printed circuit board design of the wearable sensor. We designed for minimum size and optimum manufacturing cost. Communication on board relies on low-speed I2C or SPI buses, which do not need impedance control, so we don't need an expensive 4-layer board. If the ICESP connector over here is clipped off, the board area is about 0.8 inch by 1.0 inch. To minimize footprint, the power electronics and the biometric sensors are placed on the bottom of the board, which is convenient for biometric measurements. For the power circuitry, it is very important that minimum heat is generated while charging. We experimented that no sensible heat is emitted while it charges on our skin. The charging power is well below the maximum limit of chosen components. Here you can see the main microcontroller, which is a NRF 52833 by Nordic Semiconductor. It is an ARM M4 microcontroller with a Bluetooth Low Energy module built in. Around the main microcontroller are some of the rest of the power circuits as well as the battery connector. Because of the variability of wireless power system, the power architecture is not straightforward. Here is the block diagram of the power system. The voltage harvested from the receiver coil varies in the range of 5 to 15 volts depending on distance to the transmitter. Using a buck boost converter, the voltage is stabilized at 5 volts to power the LiPo charging IC. The LiPo outputs between 3.3 to 4.5 volts to a LDO, which powers the microcontroller and the sensors. Wireless power transfer is done with RC resonant circuit. This is the design schematic of transmitter and receiver circuit, simulated as a transformer. Parasitic capacitance of the power MOSFET are used. The oscillation frequency is about 1.5 MHz, dependent on the distance, and power received on the load is 100 milliwatts. While there are standards such as Qi or AirFuel, we chose to develop our own wireless power. The quality factor of liquid metal coil is around 10 due to high resistivity of liquid metal, which is about 20 times more than copper. Existing system for cell phone wireless charging outputs too much power for microcontroller needs, which would result in short recharge time but also emit a lot of heat in the coil. We are willing to sacrifice the charging time for a lower power to ensure safety. The 100 mAh battery on board takes 5 hours to be fully charged by our system. We designed the power transmitter to be thin and flat to fit under a bed sheet or pillow, so the sensor can be charged while patient is sleeping. By increasing the resonant frequency to 1.5 MHz, we can charge efficiently at a distance of about 0.7 inch.
Here's a demo of our mobile app. When a user first logs in, they will be able to see the current temperature measurement. If the value is higher than normal body temperature of 97 to 99 degrees Fahrenheit, it will be displayed in red to alarm the user. It will be displayed in black otherwise. Under History tab, the user will be able to see the real-time graph of measured data to get a better sense of patient's temperature profile. Under the Info tab, user can update patient and doctor information to keep the information up to date.